Ever find it challenging to develop new features in small increments? Then welcome to today's episode of Time to Code, where we will tackle this challenge hands-on. Together, we will integrate a new feature into an existing application, using the smallest increments possible to maximize the benefits of continuous integration and fast feedback. Let's go! The application we want to extend is a web application we have developed in the previous episodes, which provides a wiki-style interactive navigation between diagrams. You can find the link to the GitHub project in the description below the video. Today we want to improve the usability of this application by integrating a simple full-text search feature. As this feature is pretty independent from existing features, it is a perfect opportunity for test-driven development. We start by writing tests to specify the expected behavior of the new feature. We focus on simple and easy to understand tests, keeping all relevant aspects in the tests, like the page content, and we keep all irrelevant details outside the tests, like the concrete syntax of the documents. The document builder is a small utility abstracting the details of how to create realistic Draw.io scalable vector graphic documents with elements having a caption. The fake document store is the simplest possible implementation of a document store using an in-memory list of documents. The basic idea at this point how the full-text search could be implemented would be: we fetch all pages from the document store, search the document content, and return the names of the matching documents. Okay, the code compiled successfully. As the tests will not automatically be executed right now in the CI/CD pipeline due to the explicit attribute, we will submit our changes, allowing the team to provide first feedback on the tests, for example using a code review. Now we will use the simplest implementation possible to make all test cases green. Therefore we fetch all the pages from the document store, we then search the document content, and finally return the names of the matching documents. To search the document content, we first extract the caption of each diagram element. We then use an existing component, the SVG caption parser, to extract the display text from each caption. As the full-text search now requires an SVG caption parser, we also need to adapt our existing test cases. We could use a dynamic mocking library like mockq to create a fake caption parser, but given the current implementation, it is much simpler to use the real one. Now let's remove the explicit attribute and run all the test cases. All test cases are green, so let's submit the changes. So far we got only feedback from our test cases. Now let's get some user feedback before doing any further improvement. Therefore we add the new full-text search class to the dependency injection container, and we provide a new web API called search. Now let's provide the simplest UI integration possible, which enables us to get some end-to-end feedback from our users. Therefore we create a simple input field where the user can enter the search text. We also provide a place to show the search results. These results will be clickable. We then provide two methods. The onSearchEnter method will be called when the user hits enter in the search input field. We will then call the backend API and show the search results. The onSearchResultSelected method will be called when the search result will be clicked. Now let's test our new feature in the UI. Let's submit the changes to get our first end-to-end feedback from our team. After submission we got our first feedback. It would be great to see the matching captions along with the page name in order to get some context why a certain page is in the search results. As this improvement involves a breaking change, the full-text search now needs to return some data structure instead of just the page name. We will split this change into even smaller parts. First we isolate the breaking change. We introduce the search result data structure without introducing any behavioral change. In this step, we do the minimal changes necessary to make the test cases green again. Also in the web UI we do the minimal changes necessary to keep the web UI working. Let's quickly test the change in the UI and submit the changes. Now we can introduce the actual change, and we will again use the approach of test-driven development. Unfortunately, the equals implementation of a record does not support deep equality comparison with collections, so our test would fail with this intuitive approach. So we use a small trick. We serialize the expected result and the actual result into a JSON string and compare those two strings. Now we can change the implementation of the full-text search. From all the captions we have found in a given document, we first try to find all the captions matching the search string. And if any matching captions have been found, we return those along with the page name. Let's run all tests and submit the changes. And finally, we adapt the UI to complete this change request. Therefore, we add a small section which shows all the matching captions. Let's test the new functionality in the UI as well and submit the changes. Testing the new functionality in the UI shows an uncovered scenario. In case a caption exists multiple times on a page, it is also shown multiple times in the search results. Let's fix this. We start by adding a new scenario where a page has a caption multiple times, but we only expect this caption to be listed in the search results once. Now with the test in place, let's fix the implementation of the full text search. We only need to add the distinct method to the link queue expression finding all the matching captions. And again, let's run the tests and submit the changes. Now it's time to do some code cleanup. The simple implementation of the full text search resulted in some code duplication regarding the extraction of captions from diagram elements. We resolved this duplication by moving the respective code into the SVG caption parser. Let's run all tests and submit the changes. Even though the code has been improved, we can still find some code duplication worth removing. Therefore, we introduce a small utility called SVG extensions and we move the respective code over there. And again, let's run the test cases and submit the changes. Now the feature is working as expected and the code is clean. At this point, we could think of optimizing our simple search implementation. Of course, we should measure first whether any optimization is needed, but parsing every document again and again for every search request is clearly a waste of resources. So let's improve the implementation by extracting all captions of a page once during upload and store those separately in the document store. As this change impacts multiple classes, we again break it into smaller steps. Today this application uses two types of documents: the raw document containing no parsed content and the SVG document containing parsed content. Before we can add the extracted captions to the SVG document, we need to refactor the drawing workbook implementations used to extract SVG documents during upload to use the raw document instead of the SVG document. This change causes all kinds of minor ripple effects. But the major change is in the SVG processor, which now consistently needs to parse all documents, the newly uploaded ones as well as the already existing ones. And one more time, let's run all the test cases and submit the changes. The next step is again to isolate the breaking change by introducing the captions into the SVG document without introducing any behavioral change. This change requires the introduction of a private data structure in the SVG processor to remember all information when processing the documents during upload, which is then also used to fill the SVG document with all the captions of a page. And as usual, let's run the test cases and submit the changes. After this refactoring, we realize that the SVG document actually does not need to store any XML. So we rename it to process document and change the content type from XML to string. We then fix all the ripple effects and, you have guessed it already, we run all the test cases and submit the changes. Finally, we change the document store to work with the process document and to store the captions separately. With the additional logic in the document store in place, let's also add some basic tests to see that the serialization works as expected. Of course, the change of the document store interface causes all kinds of ripple effects, but let's skip those details for now. Instead, let's adapt the full text search. We can now remove the SVG caption parser and work with the captions provided by the process document directly. And of course, we run the test cases and submit the changes. With the improved performance of our web API, we can now also improve the user experience of our application by providing search results already while the user is still typing. Therefore, we simply introduce another event handler which gets called whenever the text changes. When the handler gets called, we simply trigger the backend API if the text did not already change again within 250 milliseconds. As this change only affects the UI, which we have already tested, we do not need to run the test cases, but submit the changes directly. If we now observe that the web API is still not fast enough for this interactive search, we could introduce a simple decorator to cache the pages. To use this decorator, we simply change the composition of the application like this. Now the full text search is definitely much faster, but this solution effectively holds the entire document store in memory. Is this a good design? What if we upload hundreds of big diagrams? Answering these questions is a topic for another video. Until then, happy coding!